Huynh comes from Vietnam. He is a PhD candidate here at the University of Illinois at Urbana-Champaign. Received his Bachelor of Science from University of Minnesota, Twin Cities in 2013. Master of Science from here at University of Illinois in 2016, both in electrical and computer engineering. His research interests include high power AC to DC conversion and power system dynamics and stability.
Thank you, Aaron. Hello, everyone. Thank you, everyone, for being here today. Listen to my talk. So today I will present my research starting since last year. And the topic today I'm presenting is a theoretical analysis and experimental validation of an AC to DC system. I would like to thank Professor Banerjee, my advisor. Thanks for working with me since last year. And I would also to say thank you to Patrick Wang. He graduated from UFI, and he did a lot of work in setting up my experiment, my test bed. Does it go back? Oh, here. Yeah, so first, let me try to motivate the reason why I'm working on high power AC to DC conversion. So everyone will see that the transportation, electrification, and the renewable energy are the major trend in the power and energy research nowadays. We have heard a lot about car electrification. In this group, we're working on airplane electrification, and actually in the U.S. Navy, they have looking into the ship electrification. In a recent effort, this ship they call the DDG-1000 destroyer, and this is the first fully electric ship in the fleet of U.S. Navy. With the fully electric ship, it means that you only have one electric power system on the ship, and that is in charge of both propulsions and all the load on the ship. And for this one, the total generation capability is 78 megawatts of electric power. So I did a rough calculation, and 78 megawatt is sufficient for a little town of about 60,000 homes. So that is how big this thing is. The next thing is in the renewable energy. We also see like an uprising of the wind farm. There's a lot of huge wind farm is being constructed around the world. And in this example, this is the picture of some wind turbines in the London array. It is like 30 kilometers offshore from the shore close to London. And the whole wind farm here, the power rating is 630 megawatts. That is huge. So the common theme between the two is either for electric ship or for wind farm, we all need the megawatt scale conversion for electricity. And another common thing is for both of them, the load is all, the power it consumes or it generates is not always at 100% of the rated load. So for example, for the ship, if you design a system to like run the ship at full speed, but the ship is not always running at full speed. So most of the time, it only run at partial load. And for wind turbine, not 100% of the time you have the wind blowing at the full speed. So most of the time, a wind turbine will run at a partial load. And there's actually study that if you allow the generator on the ship to run at variable speed, and if your load is just at partial load, which is the case I just mentioned for the ship, the conversion efficiency can increase from the blue line to the purple line. If you operate at most of the time at 0.4 of the rated load, the efficiency improvement could be like up to 3%. And people already also show that in the wind farm, if you allow if you operate the wind turbine at variable speed, then you can harvest energy in a wider wind speed range, And the net result is if you trace the blue curve, the energy yield of a wind farm operating at a variable speed will be higher compared to the fixed speed one. So in order to enable the variable speed operation, what people have done in the Navy is they propose an architecture called a next generation integrated power system. And in this architecture, you have multiple multiple gas turbine running the generator. And because the turbine is operating at variable speed, but you still want to connect multiple of them together, one way is to make a AC to DC conversion and connect all of them on the DC side, and using a DC bus to feed all the load that you need to. And the common and for here clearly we need attach a big AC to DC converter to each generator. And second, if we look into the offshore wind farm DC grid, so currently almost all the wind farm that I know of is still using AC grid. But in the future, people show that if you shift the wind farm further offshore, then you have more steady wind speed, so you can harvest more energy. But the problem with shifting the wind farm to offshore is you cannot use the AC transmission line, because the AC transmission line running under the sea, the cable is very close together, so the capacitance between the winding is high. If you transmit power like under the sea for a long distance, you will see the voltage drop, and power delivery using AC in the sea with the sea cable for long distance is infeasible. So people looking at the DC grid for offshore wind turbine, and people have proposed multiple architecture. Namely, I'm listed some here and more in this paper. And the common theme for all of them is they all convert AC power to DC power at all the generator. So looking at the two architecture, we see that if we move further into, well, when we go into the future, AC to DC conversion at high power is something necessary, and that is where I'm trying to make my contribution here. It is I'm looking into an integrated method to design AC to DC system, which look in power electronic, control, and also electric machines. And what we are targeting is a system that is cheaper and higher efficiency and also higher reliability. And this is the architecture I am investigating. For a long time, people look at a generator and they'll only look at the three-phase system, three-phase generator. But we think that there's no restriction that we cannot have a three-phase port out of a single generator. And if we have multiple AC port out of the generator, we can use some of them to feed the passive rectifier and one of them to feed an active rectifier. The reason we pick the passive rectifier because that is simple. It only comprises of 6 diodes, and we don't need to do any control on the passive rectifier. We just feed voltage into it, and it converts AC to DC automatically. But the downside of the passive rectifiers is we don't have control over the amplitude of the DC bus voltage, because the DC bus the output here is depend on the voltage you apply on the AC side. And because we are looking at the variable speed operation, so the back EMF produced by the generator will depend on the operating speed. So the result is the DC bus on the DC voltage on the passive rectifier will vary depending on the operation speed. So we need to attach an active rectifier in series with the passive rectifier. One property of the active rectifier is it can regulate its own DC bus voltage to virtually any value that we want it to regulate. So in case the voltage is dropped on the passive rectifier, the active one can increase its own voltage to regulate the DC bus voltage at always a constant value across the whole operating speed range. So that is the idea. So the key message here is we want to combine something cheap, reliable, passive rectifier to convert a portion of power, and we use the active rectifier to process the portion of the power and at the same time to regulate the DC bus. So up to here, you have any question? Yeah, if you have any question, just stop me.
So your speed is determined by the prime mover?
Yes, that is true. So the speed is determined by the prime mover. If it were the case in the wind, it actually depends on the wind speed. If it were the gas turbine, it depends on how much load you are serving, and you decide the speed of the prime mover. Yeah.
So your active rectifier controls the current flowing in and out?
So the control algorithm is built on the current control, but what it tries to regulate is it look at how much voltage is generated by the passive rectifier, and it know what is the value of DC bus voltage the system needs to regulate. You take the difference will be the voltage the active rectifier need to provide, and the active rectifier actually run a voltage control loop. But the voltage control loop, if you go deeper, that is actually based on like the D-axis and Q-axis current control.
How many loops do you have in this control?
2. Current control and voltage control. Yeah. Yes. So for the rest of presentation today, I will go through analysis and design and then the experimental result. The analysis is the first we want to look at how much voltage they actually support by the active rectifier. So if we look at the conventional architecture with only one AC port, so throughout the operating speed, the active rectifier always have to support all the DC bus voltage. But if we series connected this active rectifier with the passive one, at the rated speed, and if we do 4 AC ports, meaning we have 3 passive rectifier and 1 active rectifier. So at the rated speed, we calculate and see that it only need to provide like 25% of the DC bus voltage. And as the speed decrease, what happened is the back EMF of the generator decrease, and that leads to a decrease on the DC bus voltage provided by the passive rectifier. So in order to maintain the DC bus voltage at a constant value, the active rectifier has to increase its DC bus voltage, so the sum of the two still stay at 1 per unit. So we see that, okay, so the gain of this architecture, first of all, is we need an active rectifier rated for like at max like 60% of the DC bus voltage. So 40% reduction on the switch rating. That is the first gain for this architecture. And if we look at the voltage, then we have to look at the current. And so the current here in this plot, we plot the current, the AC line current of the active rectifier versus the operating speed. And we see that for the one AC port, the AC line current follow a cubic curve because we're considering the wind load profile. And you know, in the wind load profile, the maximum power you can extract from the wind is proportional to cubic of the wind speed. So this is the profile when we have only one port. But for the 4 AC port, we have increase the current required rating for the active rectifier. And we say, okay, so this point, if we gain something on the voltage and we lose something on the current, so what do we actually gain? And if you recall, for a semiconductor device, the voltage rating is proportional to the length of the semiconductor, and the current rating is proportional to the area of the cross-section area. So it will be fair if we look at the product of the two, which means the volume of the semiconductor. So if we look into, we take the maximum current multiplied by the maximum voltage support by the active rectifier, then we will get a sense of how big is the size of the device. And we do that for all the number of AC ports ranging from 1 to 9, and we plot out the VA rating, which is calculated by the way I just showed you. And it ends up, we see that if we use 4 AC ports for the Huynh case, then the VA rating will be lowest for the active rectifier. So this is an odd again for this architecture. You have the lower voltage support by the active rectifier, and at the same time, you need the lower size of semiconductor as well. And yes?
Sorry, when you're looking at the active rectifier part, are you focusing on that because the assumption is that that is less efficient than the passive diode rectification, or is it just because that's where all your device cost is?
So we look at you asking like the assumption we make on the active rectifier?
Yeah, I'm just like, this is a different power space than I'm used to. So is the reason why you want to minimize your active rectifier because of the cost or efficiency, or what's the desire to do that?
So we want to minimize the active because of both reasons. The first is the cost of active rectifier is way higher compared to the diode bridge. The second is at higher voltage and higher power. It turns out that the diode is way more efficient than the active rectifier. The reason for that is when you run use the active rectifier, you have to deal with the switching loss, and you also have the voltage like the RDS on of each switch, and that adds up, and that's proportional to the current. The RDS on depends on current. Compared to the diode, the voltage drop across the diode device is, usually if you go to the diode I'm looking at, that is 1.2 volt, and that is almost independent of the current level. And if you think about, if you have an application of 1000 volt and the drop across your device is 1.2 volt, then you have like 99.99% efficiency. 99.9. So that is like huge improvement. So does that answer your question? Yes. When we look into the power process by the active rectifier, we see that if we only have one AC port, this is how much power needs to process by the active rectifier. And if we have 4 AC ports, because a portion of power is supported by the passive, so the active only need to support like a portion of the power. And by reduce the amount of power processed by the active rectifier, we actually gain the efficiency. So this goes directly to your answer. So this is we do calculation based on a system of I think like 3 megawatts, 3 megawatt system. And if we do only one port, the lower curve is the efficiency. And if we combine with the passive rectifier, because the diode bridge is like more efficient, so combine all of them, we actually shift the efficiency up, like across the whole operating range. Yeah. So this is another game we have for our architecture. So when we go to that point, we like really excited, and we say, let's go to the lab and test it out to see if it's actually true or we have a big dream. And so for the test bed, if I think most of you will see my bench in the lab, and that is a little like messy. But if you draw it out, what I actually implemented is this is a prime mover driving a multi-port permanent magnet. And for the permanent magnet, we feed some passive rectifier, and I use a TI box to make a active rectifier and series connect all of them and feed the load. And we also have the measurement board to perform control. So I think the coolest thing in my setup is actually this guy. This is the motor, and what the motor has. So it actually comes from a washing machine. It has this is the pre-phase And each phase have like have 12 of these little windings series connected. And what I did is I just come in and chop all the connection and get access to each individual port in this motor and make the external connection to the banana jack here. So if you see like one black and one red and black, that will correspond to 2 terminals for one winding. And the red is the phase A, green is phase B, and blue is phase C. So for each phase, we have 12 windings. It means that I can configure this machine to like 1 port, 2 port, 3 port, 4 port, 6 port, or even go to 12 ports. So that using this way, this allow me to test the VA rating, the efficiency versus number of AC port, without having to go to design a new machine. The good thing about this motor is it have multiple ports, but the downside is have a high resistance and high inductance. High inductance. So my theoretical analysis you see above will be adjusted a little because of these parasitic inductance. But nevertheless, after I adjust that, and you see here when I measure the VA rating, the yellow dot is what I actually measure, and the blue dot is the theoretical prediction. So we see that it's pretty matched with the theoretical prediction. And I want to emphasize that because of the parasitic elements effects, then the optimum number of AC port to minimize VA rating is actually moved from 4 port to 2 port, but nevertheless we still see the trend. So in using this architecture can actually minimize number of AC port, minimize the VA rating for the active rectifier. And we also test the power process by the active rectifier. The solid line is the predicted value from the theoretical calculation, and the dots are the one that I actually measure from the test. And we see that so the blue line is for only use a TI box and the active rectifier. And if we combine with the passive rectifier, we can actually reduce the amount of power processed by the TI box. And 2 ports correspond to the red curve, and like the yellow is 3 ports, and the purple line is 4 ports. And how is it compared to the theoretical, the ideal case? So for the ideal case, we see going from 1 port to 2 ports will have the reduction of 50% of power process. However, on our test bed, we only see like 30% of reduction. That is because the high inductance of the machine. So when the diode bridge, the voltage support by the diode bridge will be lower than the ideal case. So to keep the DC bus voltage to constant, the active rectifier has to maintain the DC bus voltage higher than what it should have done in the ideal case. But nevertheless, our theory can accurately predict the behavior of the system. So that validates that this is a trustworthy result. And also, I also measure the conversion efficiency. And the lower line is the efficiency for TI box. That is typical at the rated condition. The conversion efficiency is at 94%. And if we combine with another passive rectifier, it can boost up the efficiency by like another 2%. So that is lead to like 30% reduction in conversion loss. And that is matched pretty well. The shape is matched pretty well with the theoretical prediction. So if you can see the similarity between the two. And this point concludes my talk today. I'm open for question. Yes, Aaron.
For that last plot, was that the efficiency of just the TI box or the TI box plus the passive rectifiers?
This is the whole system conversion efficiency.
Okay.
Yeah. I measure how much power go in the conversion system and how much go out and take the diffusion. Yes.
How do you maintain the power balance in that stack? You've got a series stack of basically 3 different sources, 4 different sources, and they're at different voltages, but they're series stacked, so they should be sharing current if I'm looking at that correctly.
Yes.
So how does that work?
Yes, so that is a very good question. My answer is we don't care about power balance now. We just take the active rectifier and try to maintain the DC bus, try to maintain the net DC bus voltage to be constant, and whatever current pushed out by the active rectifier will be matched by the diode bridge because that is a series connection.
But is the power coming out of each one of the different AC ports the same?
No, it doesn't. It doesn't have to be the same. For each port connecting to the diode bridge, they will be the same, but they would be different from the port connect to the active rectifier.
And I guess from a motor standpoint, right? It's the same number of windings going through the same speed and everything else like that.
Yes.
So where's the power going?
So effectively, you'd have some kind of torque pocket, right? With a small set of you're trying like imbalance using the active rectifier, you're driving imbalance mode.
Yeah. So yes, if we look into like compare each individual port, we could run into the issue the power on each of them is like not imbalanced. But if we like evenly distribute the winding across like around the rotor. So for example, if I have like 3 series winding to support the active rectifier, I will put one here, and one there. And the next is like that is 120-degree apart, then it will balance out. All of them will balance out. Yeah. So, but that is a really good question as well.
You mind Andrew's question about like why are you doing this, as far as like the trade-offs between efficiency and cost. You might work up like 2 slides like at the very beginning that do like a plot of like currently available passive rectifier technology, currently available active rectifier technology cost and efficiency trade-offs. And then you would just like plug those slides into every presentation you do until you graduate. That's just what happens.
Yeah.
Because otherwise, especially if you're dealing with people that do lower power stuff, they're going to be wondering why. Because typically, an active rectifier seems to be a more efficient solution in power electronics.
Yeah, as a low power scale, yes. But when we look at like high power, then the story is
so
different.
You probably want to clarify that. And I guess on that note, I would ask, can you give me an explanation as to why even using the low power MOSFETs in that device and low power passive rectifier, you saw efficiency gains? Because that's actually kind of surprising to me.
Yeah, so
Your voltage for your power was all that 200 watts.
the voltage I'm doing now is the voltage is 300 volt. That is the net DC bus voltage is 300 volt.
Okay.
Yeah, and the diode drop I having is like the voltage drop across the diode is like 1.2 volt.
Those are in series, effectively, right? Those diode drops are in series.
Yeah, they're in series.
So it's like,
yeah. So if we look at the diode bridge alone, and I measure the efficiency for the diode bridge alone, that can reach like 97% in my application. And the typical efficiency of the TI box is 94%. So if we combine all of them, combine the diode and the active, the efficiency will go somewhere between like 90, 94, 97. So that is why we see the efficiency gain. Yeah.
it also probably has to do with the trade-off between current voltage and the power. Because if you were to
Mm-hmm.
then your losses on the diodes would be higher.
If we raise the current, the
If you
drop,
raise the current for the same voltage, the trade-off might be a little bit different.
raise the current for the voltage.
We can talk about that.
Yeah, we can talk offline on that. Yeah. So you have any more question? So if not, then let's Olaolu start his talk. Yeah, thank you everyone again. Yeah, let me introduce Olaolu. Olaolu is from Lagos, Nigeria. Olaolu is from Lagos, Nigeria. He's received a BS degree in Electrical and Electronics Engineering from University of Lagos in 2010 and a master degree in Electrical and Computer Engineering from University of Illinois at Urbana-Champaign in 2014. He's currently working toward the PhD degree under the supervision of Professor Alejandro Dominic Garcia and Professor Pete Sauer in Department of Electrical and Computer Engineering at UIUC. His research interests include microgrid modeling, analysis, and control, and hardware implementation of microgrid control architectures.
Thank you for that introduction.
Okay, thanks for coming to this talk today. And today I'll be talking about the library of second-order models for synchronous machines. I'm going to start off with an introduction, after which I'll discuss the model derivation procedure. Afterwards, I'll introduce the second-order models we developed and give some numerical validations for them. And finally, I'll conclude with a summary and some concluding remarks. So dynamic models of synchronous machines and power systems in general find applications in power system analysis, control design tasks, as well as in education. For example, system operators use models for power system security assessment. Engineers employ models when developing microgrid technologies. And educators utilize models as tools for teaching students how microgrids operate. And all these different applications require models with different levels of detail, complexity, as well as computational cost. And in the literature for dynamic models of synchronous machines, there's a proliferation of synchronous machine models with varying degrees of details, complexities, as well as computational cost. For example, there's the high-order model, which is the most detailed synchronous machine model. It includes dynamics of most machine components. There's the two-axis model, which is a ninth-order model. It's similar to the one-axis model here, but it includes flux dynamics for one damper winding. The one-axis model, on the other hand, is an eighth-order model that neglects stator flux dynamics and damper winding flux dynamics. The classical model, which some of us may be familiar with, is a second-order model. It's commonly referred to as the simplest synchronous machine model, and it only captures dynamics of the angle as well as the speed of the generator. And these are some references that talk about these models. And so let's delve deeper into the classical model. It's a second-order model. What second-order means is that it has a state space dimension equal to 2. So here we see the angle as well as the speed. And you can also think of this model as a constant voltage behind a reactance. And so analytically, like I said before, this is the simplest machine model. However, it is only useful for first swing stability analysis. What this means is beyond the first 1 second, this model starts to fail. And so with all these in mind, due to these limitations of the classical model that I discussed, higher-order models, such as the one-axis and the two-axis, and the higher-order model I talked about earlier, are typically employed. However, the increased details and computational cost that these other models present makes them analytically intractable for control design tasks. And accordingly, there's a need to develop models that possess the simplicity of the classical model, but also the temporal breadth that it lacks. So we want models that are as simple as the classical model, but they can provide accuracy beyond 1 second. So an example of such control design task you could think of is maybe a synchronization analysis of a power system. If the synchronization analysis exceeds 1 second, then you can't use the classical model. You can't use the other models for that task, because when you're doing synchronization analysis to design a controller, you're only concerned with certain dynamics, the angle and the frequency. And so we want simple models that are accurate. So because of this, we move beyond the classical model. And so in line with this, we derived a library of second-order models. And in comparison to the classical model, they have the following form. So structurally, they're similar in the sense that there are 2 dynamic states, the angle and the frequency. However, there are some new variables we introduce. The mechanical torque is going to change. The value of the mechanical torque will change, as well as the voltage behind the reactance and the value of the voltage at the generator bus. And there's these other constants that are introduced. And over the course of this talk, I'm going to discuss how we computed values for these parameters. Any questions?
Can you explain the reason why you propose this model? Like the reason behind the K1, K2, and K3?
I'll get into that. I'll get into how these terms came about. So we didn't start by assuming this form. We ended up at this form. So I'll talk about how we got there. Okay. And so the method we use to arrive at that form is called singular perturbation analysis. And to delve deeper into that, we first need to define a big O notation. So for some positive constant epsilon greater than 1 and some function of epsilon defined on some subset of the real numbers, we can write that function is order epsilon I if and only if there exists a positive real number C such that the magnitude, the absolute value of f of E is upper bounded by C epsilon I as epsilon tends to 0. So something to just take a note is this big O notation. If I say something is order epsilon I, this is what it means. It means you can find some constant C that bounds that function in the following way.
Can you explain what does this physically mean?
This means I can find, if I have a function, well, physically it's tough to describe it physically, but I can define it geometrically. So if I have a parabolic function, right? I'm saying that I can find a constant C that multiply. It's a parabolic function as a function of epsilon. Let I be equal 1. I'm saying that I can find a constant C whose value is always greater than the value of that parabola at all points. So say, a simple example is a straight line that's above the parabola. So that straight line will always be greater than the parabola, right? So I'm saying as epsilon tends to 0, that straight line will always be greater than the parabola. Okay. And so if we consider the following 2-time scale dynamical system with some fast dynamic states and some slow dynamic states, let X denote the slow dynamic states and Z the fast dynamic states. We can define the following terms, T and tau, where T and tau are related by this form. Now we put some conditions on F, just some regularity conditions, and then we say that F is order 1 and G is order 1 according to the previous definition. So if we can come up with a dynamic system of this form, we can make this assumption that x and z can be decoupled into some slow component and some fast component, and same for z, slow and fast, where the bar and tilde denote a slow time scale and a fast time scale.
Is order one thing you just bound it as epsilon goes to 0 by linear
Correct.
goes to 0?
By constant. Yeah, by constant. That's what it means.
Are you in some sense linearizing it? Or
No, no.
oh, but order one is a straight line.
Yes. So I'm saying that basically as epsilon goes to 0, you can find some constant that upper bounds this. That's what I'm saying. Okay. And this singular perturbation analysis is discussed in details in this book by Peter Kokotovich. And so given those assumptions and that system, this theorem is formulated that if the dynamic system that I described earlier satisfies some stability conditions when epsilon equals 0, then the solution of that system is given in this form. x0 plus some other epsilon term, and z of t is equal to this plus some other epsilon term. And in addition, there exists a certain time after which this term goes to 0. And so this is what we use. And simply put, the dynamics of these two terms, the slow term and the fast term of z, can be described by this, where this is the slow component and this is the fast component. So all we've done right now is we've taken that time scale, two time scale dynamical system, and we've divided it into a slow term and a fast term. That's all we've done here. And so we utilize this singular perturbation analysis to develop that simplified models. And so this is how we did that. Using developments in the literature, we developed the 19th order synchronous machine model, which was very detailed. It included dynamics for damper windings, the excitation system, the governor, the engine, and all of that. And we took that 19th order model and we identified the fast and the slow dynamic states. And we identified that these were the fast states. After identifying the fast states, we expressed the 19th order model in this form, where all those fast states were put in Z and all those slow states were put in X. And after doing that, we replaced the differential equations corresponding to the fast dynamics, which is this, with algebraic counterparts. So if you think about it, if we can replace this with algebraic equations, it simplifies the model to just this, right? Because we can substitute all the algebraic solutions for Z in here, and we're left with a reduced order model. So that's what we did. And
How did you decide the value of epsilon?
great. It depends on the time scales we're concerned with. So if we're concerned with 5-second time scale, the value of epsilon we chose is 0.1. And we can talk about how they relate, but epsilon depends on the time scales we're concerned with. So for synchronization studies, which is why we developed this model, we're concerned with much higher time scales, like 2-3 seconds for. So we chose 0.1 based on the time scales we were concerned with. Okay.
If you go back, these are all fast states, and the diesel engine is listed as a fast state. What were some of the slow states?
The slowest states were the angle and the frequency, which the classical model correctly predicts. Yeah.
Okay.
So you can actually have different approximated models depending on what time scale you're looking at.
Correct.
As a threshold between high speed and low speed dynamics.
Correct. Yes. And so what we did to reduce the models is we took all the differential equations corresponding to those fast states, and we replaced them with algebraic counterparts, which are known as approximate manifolds. And So one example of a manifold is what they call a zero-order approximate manifold. And all that consists of is if you have some function differential equation in this form, you can express it approximately in this form. If you're doing a first-order approximate manifold, if you had a differential equation in this form, you express it in this form. If you compare these two, you see there's just the first-order term being added. And likewise for the second-order approximation. So all we just did is identify the fast states and replace them with approximate manifolds. And so when we substituted these approximate manifolds into the differential equations for the slow states, the result was the dynamic model that you had a question about earlier on. So that's how we came up with this form. And so now I'm going to talk about the models that we developed. The first is what we call the elemental model. We developed that by replacing the differential equations for all the fast dynamic states with zero-order approximate manifolds. The result of that was we found that K2 and K3 is equal to 0. So if you compare this to the classical model, it has a very similar form, except there's a constant voltage here. So this is what we call the elemental model, the semi-damped model. We developed this by replacing the differential equation describing the slowest damper winding state with a first-order approximate manifold. And then we replaced the other fast dynamics differential equations with zero-order approximate manifold. The result was K3 alone is equal to 0. So what this basically corresponds to is the contribution of the damper winding in torque, the damper winding torque to the operation of the machine. So if you think about it, the damper winding only kicks in when the frequency of the generator, right, is not at the nominal level. So if you think about it, when the frequency of the generator and the frequency of the bus, no, this is something else. This should be theta. This should be theta dot. So when theta dot and this are equal, this contribution is going to go to 0. So the addition, the usefulness of this model is just that it captures the effects of the damper windings. We developed the damped model by taking it a step further. We replaced all the damper winding states with the first order approximate manifold and replaced all the other dynamic states with a zero-order approximate manifold, and we got this form. Any questions?
So you're saying that theta dot is theta dot, right? Otherwise it's
Yes.
always constant omega.
Correct, yes. This is supposed to be theta dot. Sorry. It's supposed to be theta dot. Yeah. So using this model, we can capture the effects of the damper winding. That's the nice thing about it. And so now some numerical validation. Now we're going to compare the models we developed with the higher order model and the classical model to see how well it performs. And so we use this simple two-bus example. We have the generator here, which we're going to model using the higher order model, and then we'll model it using the classical model, and then we'll model it using the library of models we developed. And then we're going to vary the power demand at this bus and see how the responses of all the models compare. So case 1. We start with a stable equilibrium point for the higher order model as an initial condition for all the models. And then we change the power, the real power demand at the bus at 30 seconds. And this is the response we got. As I mentioned earlier, you can see that after 1 second, the response of the classical model deviates drastically from the others, right? And then zooming in, you can see how our models compare with the higher order model. We can see that the error is minimal. So that was a good thing. And this is for the frequency of the generator.
Does that see what the y-axis is of this?
The y-axis is the frequency in revolutions per minute. Yeah. We looked at the power angle also, the angle of the generator, similar response. There should be one more, and also the voltage. So if you know about the classical model, it doesn't do well with estimating the voltage of a system. So that was what we observed, but our models perform nicely. So that was case one, comparing the classical model, the high-order model, and all the models. Now we want to compare all our models to the high-order model and see if the first-order approximation makes much of a difference. And so utilizing the stable equilibrium point, we make these changes at 30 seconds and the rest. And I'll come back to this result, but let me just show the plots. This was what we got. The frequency of the generators, they match nicely. Zooming in, you can see the error is minimal compared to the high-order model. Same with the voltage and the angle. So we took it a step further and we computed the root mean square error for all these models. And if you look closely, for the angle and the voltage, they're very close. The first order approximation doesn't change much. But for the frequency, we see that the error for these two models is significantly less than that of the elemental model. And we can explain this because these models are taking into account the effect of the the damper windings. So that's just that. And in summary, we introduced the library of second-order models for synchronous machines that have a similar structure to the classical model, but they can be utilized for stability studies beyond 1 second. The models we developed are the elemental model, the semi-damped model, and the damped model. They were developed using singular perturbation analysis to reduce the 19th order high-order model to the second-order models. Thank you. I'll take any questions now.
How do these models compare in complexity and I guess accuracy compared to some of the original models you listed up there, like the 1-axis and 2-axis?
Yeah, in terms of complexity, the 1-axis is 8 order, so 8 dynamics. So in terms of complexities, ours is just 2 orders. So if you were simulating a very large power system, you can see how that will multiply. In terms of performance, we didn't check with them. We checked with the high-order model instead. And since our models perform well compared to the high-order model, assumption is they would perform well in comparison to the 2-axis. But that's something we could look into.
I think
just
not
yeah.
comparing to yourself, but comparing to something else like that. Like especially if you're competitive with that, like you said, your complexity is so much better.
Yes.
Or lower.
Yeah, lower.
If your accuracy is similar, then that's a win.
Okay. Thanks.
So you have compared models to models. Have you ever had the chance to compare the model to any PMU data?
So any PMU data?
Yeah, any like actual recording on the system because there's a chance that all the models are wrong.
Yes, correct. Someone said all models are wrong, but some are useful. So no, we have not compared them with PMU data. The closest thing to a real system that we compared it to, however, was something called ultra-high fidelity models. And they're models that are even more detailed than the high-order model. And it's our collaborators at Typhoon HIO that provided us with those models. We compared them with them.
Can you go to slide 13? This is more of a, I think it's just, if you go to slide 13. Yeah, when you say it's a 19th order synchronous machine model, oh, not this one. Go to the next one. Sorry, I think you are 13. So when you are including your speed governor, diesel engine, excitation system, it's not just anymore synchronous machine. It's a system like the entire prime mover generator system. So when you are saying it's a 19th order synchronous machine system, to me it's bothering me a little bit because I can't see its 19 states in the synchronous machine itself.
Okay.
It's more of the entire system, which includes your control, probably some controllers are there.
Yes, that is true. Yes,
so when
correct.
you are talking about 19th order, I would prefer to say it's like a generating system rather than just synchronous generator.
Okay. Yes,
but
it
it's
does.
just about terminology. But
Okay.
Overall, it was thank you. Great.
Okay, thank you. Yes.
So what
what do people do when they analyze the power system stability? Do they use this 19th order model, or they use just the most classical second order?
Yeah, for transient stability studies, the two-axis is typically used, which is a ninth order model.
Oh, nine.
Yes.
So ninth order means there are governors and everything.
Yes, correct. Yes.
But then how to figure out from systems? So today I install one diesel engine genset in my house, and it has some controller. And how do I figure out how do I use this model in real world?
Well, that's a tough question. Yeah, that's.
How will I
Yeah.
know which one is the because what
Yeah.
you're doing is very neat and very clean. You are doing a time scale separation
Yes.
of this entire system, which is great. But how do I know which one is fast? Like I install it,
Yes.
figure it out. Is there any test procedure, or are you guys planning to do anything interesting in the sense like how do I characterize this system in terms of testing? Can I figure out these states which one is faster and figure out what will be the model of a real world genset?
Okay. I can tell you how I did it, how I characterized the states. I had to look at the eigenvalues of the states and see which eigenvalues corresponded to which states. That was how I was able to say, okay, this state is faster than this one. So it was very, very very intense. Yeah. Yeah.
What are the information we need?
You need a model first, a model of the full system. So going back to your question, what I would do is I would first of all develop a 19th order model, that I believe captures out the system behavior. And then I would do some kind of parameter estimation. Okay. Okay. And then I would do some parameter estimation. Right. That's how I would do it. Yeah. And then, yeah.
Okay. Thank you.
Thanks.